Today we will study the real transformer, because in previous lecture we had started ideal transformers and some basics of the transformers. Today we will study the real transformers. In this case we will cover two sections of our textbook, 2.4 and 2.5, which deals with the theory of operation of real single phase transformers, and 2.5 deals with the equivalent circuit of a transformer. In real single phase transformer, we take a transformer in which primary winding is connected with the sinusoidal AC voltage, and the secondary winding is left open. If we see, as we know from the Faraday's law, that E induced is equal to rate of change of lambda, where lambda is the flux linkage in the coil across which voltage is being induced. So in this case we are going to induce the voltage across the primary coil. But we know that the total flux linkage is the sum of the flux passing through each turn in the coil added over all turns of the coil. Let's suppose the coil for one turn is lambda 1, similarly another turn has lambda 2, and then we have a third turn which have the flux equal to lambda 3, then total lambda would be equal to lambda 1 plus lambda 2 plus lambda 3. If we suppose it is the total number of turns are n, capital N, then it would be lambda 1 plus lambda 2 plus lambda 3 up till plus lambda n. But we cannot write it as total lambda is equal to n lambda, because every turn does not have equal flux. Every turn has different flux according to its windings and according to its position. So this is how we calculate the total flux. To calculate the average flux, we can say that average flux is equal to total flux over total number of windings, turns. So it would be lambda over n. If we put this value of lambda over n, if we put this value of lambda, which becomes average flux into n, in the first equation on this slide, then the equation would become like E induced is equal to N d of lambda over d of t, d of d of flux, average flux over d of t. So this is written in the blue color, so you can substitute the value. Now we come to the voltage ratio across a real transformer. When we apply the voltage on the primary side of the transformer, then some flux lines would go into the air and come back to the winding, and some lines go into the core and have a mutual flux with the secondary coil. In the primary coil, some part of the flux would be mutual because the flux lines would be passing through secondary as well as primary coil. As you can see over here, represented by flux phi of M, flux M. M stands for mutual. But you can also see that there are phi LP lines, the lines which are going into the air and coming back to the primary coil without going towards the secondary coil. So these lines would be leakage flux lines. L is for the leakage and P is for the primary. Similarly, phi LS secondary. So now we will see in the form of equations how we can see its equations. As we know that the average flux produced by this voltage is this, as discussed earlier, some of the flux lines leave the iron core and pass through the air. As I have told you earlier, these are the phi LP lines. The flux that goes through one of the transformer coils but not the other one is leakage flux. Already discussed this. The flux in the primary coil can be divided into two components. One component is phi M, which is a mutual flux, and another component is phi LP, which is the leakage flux of primary core. If we take the basic equation of given AC voltage from the previous slides and we put the value of the average flux in this blue equation, we get the equation on the right hand side, which is written in black color, which shows that it has been divided into two parts. First part shows the part which deals with the mutual flux, and the second part deals with the leakage flux, and it can also be written as EPT and ELPT. These are the same equations. First two equations are the same which we have discussed on the previous slide. And for the secondary side, phi of S is equal to phi of mutual flux plus leakage flux on the secondary side. On the similar lines, we can derive these equations, and we can also obtain the last equation given as VST is equal to EST plus ELST, where EST is the voltage obtained from the mutual flux, while ELS is the voltage obtained from the leakage flux on the secondary coil. From these equations, it can easily be derived that EPT is equal to NP into the rate of change of mutual flux. Similarly on the secondary coil, and now we take this NP in the top equation and NS in the second equation. We take these n's toward the left hand side, which will go in the denominator, and you will note that the right hand side would become the equal and similar. In this case, we can say that d of dt of mutual flux is equal to EPT over NP and EST over NS. But we know that EP over ES is equal to NP over NS, which are equal to transformation ratio A. In a good design, the leakage flux on the primary as well as on the secondary coil is negligible as compared to the mutual flux. If we consider phi L of P and phi L of S negligible, then we substitute the value of phi LP and phi LS equal to 0 in the previous equations, and we get this equation which shows that Vp over Vs is approximately equal to Np over Ns, which is equal to A. The smaller the leakage flux, the closer the transformer will be to the ideal one. So if the leakage flux is negligible, our transformer will be very close to the ideal transformer. Now we come to the magnetization current in real transformer. This is the same diagram which shows that the AC power is connected to the transformer, and by connecting this AC power we can see that the current flows in the coil, even we know that the secondary coil is open circuit. This is again the Faraday's law. On the right hand side you can see that there is a derivative taken for the average flux. If we want to find, or if we want to solve this equation for average flux, then average flux would be equal to E induced, or VPT, and then it would be integral, because in the first equation, in this equation, this is the derivative, and this derivative, if we shift it towards the left side, it will become the integral, and we can write E induced as VPT. So this would be the integral of VPT with respect to dt, and this NP would become 1 over NP over this side. So this is 1 over NP, and the rest is this average flux. But we know that the VPT is equal to constant Vm into cos omega t. But this cos omega t, Vm cos omega t, is substituted into this equation to get this simple equation, and after solving this integral of cos omega t with respect to dt, we will get sin omega t over omega, and this omega has come from by solving this integral. So this cos omega t would become sin omega t over omega. When an AC power source is connected to a transformer, a current flows in its primary circuit even when the secondary circuit is open circuited. Already discussed this point. It consists of two components. One is the I of M, magnetization current, which is the current required to produce the flux in the transformer core, and the other one is the I of H plus E, which is the current required to make up for hysteresis and eddy current losses. So this is the basic curve of the magnetization curve of the transformer core. In next slide we will study this in detail. So in this case we see that the first figure is showing the sinusoids of Vpt and phi of t, which means voltage on the input and flux. You can see from the below equations that Vpt is equal to Vm cos omega t, as we know. So since there is a cos omega t, for the t is equal to 0, cos omega t would become 1 and the Vpt would become V of m. So as you can see from first figure that Vp of t starts from some amplitude V of m at t is equal to 0. If we see the second equation, which is a flux equation, and the flux equation is basically consists sine of omega t in this, but we know that sine of, if we put the value of t is equal to 0, sine of 0 would become 0 and the phi or flux would become 0 at t is equal to 0. It can be seen from the sinusoidal waveform in first figure that it starts from 0 when t is equal to 0. This flux line is shown in bold form while the Vpt is shown in the dotted form. And then we see that the magnetization curve is also obtained from these values of Vpt. And the last figure is showing the I of m, and the I of m increases fastly when the magnetization curve becomes close to the saturation on plus side, either on minus side. Similarly, I of m grows up gradually when it sees that the magnetization curve is saturated. The core loss current in a transformer. One thing is I of m, which we have seen in the previous slide, the curve of I of m. Now we are going to see the curve of I of h plus e, which is basically the hysteresis and eddy current losses. So this is the current which makes up for the hysteresis and eddy current losses, and in this case we know that the main current in the coil would be the summation of this current ih+e and I of m. So now the first figure, the top figure shows I of h+e and the lower figure shows I of m. Now we are going to add both of them and get the results, and in the blue color you will find the resultant graph, which is ih, which is equal to the summation of left two graphs. So the total iex, or you can say the I of excitation current in real transformer, would be I of m plus ih plus e. Now we come to the current ratio and dot convention. Connect a load. We Now we connect a load on the secondary side of the transformer so that we can also observe the current on the secondary side. A current flowing into the dotted end of the transformer produces a positive MMF, and if the current is flowing out of the dotted end, the transformer will produce a negative MMF. In this figure you can see, in the primary case the current is flowing into the dot, so this produces, the primary side produces positive MMF. But on the secondary side you can see that I of s is leaving the dot, is going away from the dot, so the transformer will produce a negative MMF. So we say that f of p on the primary side, which is n of I, on the secondary side it is minus n of I. Similarly, the net MMF would be f of p minus f of s, which would become npip minus nsis. But we know that MMF is equal to flux into R. Entering the dotted end, the EMF will add to each other. If one current enters and the other one leaves, then the MMF will subtract from each other. For a good design transformer, R should be very small, near to zero, as long as the core is operating in unsaturated region. The R over here is referred to reluctance. So if we consider that R is negligible, we put 0 over here in this equation. If we put R is equal to 0, this right hand side would become 0, approximately 0, and it would become like this. So in this case, the F total F net would become almost 0, and if this becomes almost 0, then NPIP minus NSIS would become 0. On the other hand, we can see that NPIP and NSIS would be equal to, approximately equal to each other, and we can also calculate the transformation ratio from their calculations, from the currents and the N of S and primary. So we can also calculate A. In order for MMF to be 0, current must flow in to one dotted end and out of the other dotted end. Assumptions to convert a real transformer into an ideal transformer. So the core must have no hysteresis or eddy current. Another assumption, the magnetization curve must be an ideal one. As you have seen, the difference between the real and ideal diagram, the leakage flux in the core must be 0. There should not be leakage flux. And the fourth assumption is the resistance of the transformer winding must be 0.